Yeah, so thanks for the invitation to speak here. Yeah, so the title of this talk is Sub-flexible symplectic manifolds. So I want to start by just kind of briefly reviewing some recent developments in symplectic flexibility. So maybe the first ingredient is the notion of loose legendrians. So these were defined in Emmy Murphy's thesis, I think around 2012. So the idea is that, this is a kind of a special class of Legendrian submanifolds which live in any contact manifold of dimension at least 5. So we'll just write M kernel of some contact 1 form. And then they satisfy the following properties. So I guess such that, so first of all, any formal Legendrian is formally isotopic to a loose Legendrian. And then secondly, so this is sort of existence, and then there's some kind of uniqueness which says that two loose Legendrians which are formally isotopic are actually isotopic through Legendrians. Yeah, so here, so formal, maybe I won't give the precise definition of formal Legendrian, but it's some kind of purely algebra topological condition. So it says roughly like you have just an embedded submanifold and some kind of rotation of the tangent planes such that they become kind of Legendrian planes. And similarly here, you can think of this second condition as saying roughly that if you have, so roughly speaking, if you have two Legendrians which are just smoothly isotopic and a little bit more kind of bundle theoretic information, then they're actually isotopic through Legendrians. So you sort of get this. So what we're really after is kind of actual Legendrian isotopy, which is sort of a geometric condition, and you sort of get that for free if you have loose Legendrians. Yeah, and so far, I guess so far the way I've stated it, it's sort of just some kind of formal thing. But the main reason this is kind of a useful result is that in many cases we can really check geometrically that a given Legendrian is loose, and that tells you a lot about that Legendrian. If you have some explicit Legendrian submanifold that you care about. Yeah, so I guess, so another ingredient I'll need is the notion of a Weinstein domain. So just to set up the notation, so for me a Weinstein domain is it's a triple W lambda phi, where and this W will always be of dimension, I guess, 2n. So here W is I guess, compact manifold with boundary. And lambda is the primitive of some symplectic form. So d lambda is symplectic. And the Liouville vector field, which is the vector field dual to lambda with respect to this 2 form. So the Liouville vector field should point transversely outward along the boundary of W. And then, so finally, so phi is some Morse function. And then there should be some compatibility between phi and the rest of the structure. And the compatibility is that the Liouville vector field is gradient-like for this Morse function. Yeah, so this is sort of the natural notion of a symplectic handle body. So phi is some Morse function, and kind of everything about phi is sort of nicely compatible with the symplectic form. Like the stable manifolds are Lagrangian, and the attaching spheres are Legendrian, and the regular level sets are contact, and so on. Let's see. I guess I'll go up here. And then, so finally, let me define just the natural equivalence relation between Weinstein domains, which will be sort of relevant. So this is what I'm calling Weinstein homotopy. So it's essentially a Weinstein homotopy is just a one-parameter family of Weinstein domains on some fixed manifold W. So it's a one-parameter family of Weinstein domains, except that we allow this family of Morse functions to have birth-death, so isolated birth-death moments. Yeah, so I claim that this is sort of the natural equivalence relation to put on Weinstein domains. Without allowing birth deaths, it wouldn't be a very interesting notion, because all you'd be able to do is sort of move the critical points around. You wouldn't be able to change the number of critical points, for example. But for example, with this condition, so one basic observation is that if you have two Weinstein homotopic Weinstein domains, then their completions are exact symplectomorphic. Yeah, so it's not true on the nose that the two Weinstein homotopic manifolds are symplectomorphic, because just for sort of silly reasons, like you could change the volume or something like that. But when you pass the completion, so this means just you sort of pass from being a compact manifold to a non-compact manifold by attaching a sort of half-infinite conical end, then this equivalence is sort of strictly finer than exact symplectomorphism. Yeah, so then I can define one of the kind of main objects of study in this talk, which is the notion of a flexible Weinstein domain. Yeah, so this is some sort of parallel of loose Legendrians, but in the world of symplectic manifolds. So first, let W lambda phi be a Weinstein domain. And let's assume for simplicity that phi has distinct critical values. Just to make the definition a bit cleaner, so assume phi has distinct critical values. Yeah, so the idea is just supposed to be that, so any Weinstein domain is kind of built by some iterative process of attaching Weinstein handles. So you can show that anything of this form is given by just starting with the sort of standard symplectic ball, and then you attach symplectic handles along there's some kind of model for attaching a Weinstein handle to a symplectic manifold with boundary. And the idea is that you're supposed to be flexible if kind of all these attachments are along these loose Legendrians. And the idea is supposed to be that the sort of flexibility of these Legendrians gets extended to the flexibility of these Weinstein domains. So a bit more precisely, so we say So let's say this is dimension 2n. So we say it's explicitly flexible if for any critical point p of phi of index n. So the critical points of phi, it's easy to show that they can have index at most n, and sort of all the interesting symplectic topology is contained in the critical points of top index. So for every top index critical point, we look at the sort of attaching sphere of this critical point. So I guess more precisely, look at the sort of stable disk intersected with a small regular level set below that critical point. And then this should be a loose Legendrian. In the contact manifold, the natural sort of contact structure on this level set. And then we say it's just flexible if you can make it explicitly flexible after a Weinstein homotopy. Yeah, so then again, kind of the sort of natural parallel of Murphy's theorem is this the sort of fundamental theorem about flexible Weinstein domains, which is due to Chile-Beck and Eli-Ashberg. And so it says, so there's some sort of existence and then some sort of uniqueness. So first of all, I guess any Weinstein domain of dimension at least 6 is almost symplectomorphic. So it's formally equivalent to a flexible Weinstein domain. And then two flexible Weinstein domains in the same formal class are actually Weinstein homotopic. So more precisely, so two flexible Weinstein domains whose symplectic forms are homotopic through non-degenerate 2 forms, or equivalently, they have just homotopic almost complex structures, are actually Weinstein homotopic. Yeah, I just mean a diffeomorphism which kind of respects the homotopy class of the almost complex structure. So almost symplectomorphic just means, so for me this just means it's a diffeomorphism such that when you pull back the symplectic form of this one to this one, you get two forms which are homotopic through non-degenerate 2 forms. So it's a little bit more than just a diffeomorphism. But like in many cases, for example, it's just sort of automatically the same as just diffeomorphism. Yeah, so maybe, so I mean, kind of a silly example to keep in mind is that any subcritical, so by definition, so any subcritical Weinstein domain, subcritical meaning it has no critical points of index n. So it has sort of critical points of strictly lower index than they could have been. These things are just by definition flexible. And so it's sort of well known that subcritical manifolds have trivial symplectic topology in some sense, and then flexible Weinstein domains are some sort of extension of sort of larger class of Weinstein domains which also have trivial symplectic topology in some sense. Yeah, so any questions about the statement so far? So I guess, where's the natural place to go? Here, maybe? Yeah, so for me, I guess the kind of interesting question is if you're given a specific symplectic manifold or Weinstein manifold that you care about, to kind of ask, is it flexible or not? And generally, I guess how this goes is, I mean, these techniques are still being developed, but basically if it's, on the one hand, if you want to show, so if you can show that it's flexible, then that's sort of the end of the story, because flexible guys are just classified by sort of algebro-topological invariants. And to show it's flexible in practice, you basically just need to kind of understand the geometry pretty well, and just, you can really kind of, there's really geometric ways of showing that a given manifold is flexible. And so once you do that, you sort of win. But if it's not flexible, then you need some sort of rigid invariant that can detect non-flexibility, and that's where things get a bit more kind of interesting.
Maybe this is like skipping ahead too much, but are there examples of symplectic homology vanishing for non-flexible?
Yes, that's sort of one of the main points of this talk, actually. Yeah. So you'll see in what sense there are examples of this, but yeah. So okay. So first, I guess let me just state sort of the main theorem of this talk then. So this is joint work with Emmy Murphy. So the statement is that any flexible Weinstein domain it has, after possibly a Weinstein homotopy, a non-flexible sublevel set. So I'm just using the fact that every kind of regular sublevel set of a Weinstein domain is naturally a Weinstein domain itself, just by restricting everything. And so, for example, maybe kind of the most interesting example to keep in mind is that you can take just the standard symplectic Weinstein structure on a fine space with dimension at least 3. So take, for example, C3, and it tells you that just you take the standard structure and you homotope it a little bit, and then suddenly you have a sublevel set which is not flexible. So it has some sort of non-trivial symplectic topology living inside of it.
Is that sublevel set, does it have the same topology as the ambient space, or is it maybe different? Smooth topology.
The smooth topology, so I'll definitely talk about this more, but the smooth topology is kind of, there's some, at least with these techniques, there's some restriction on what it can be. So it needs to have some sort of non-trivial homology class. And that's kind of the only restriction. So for example, in this case, the sublevel set is going to be, well, it can't be a ball. At least I wouldn't know how to prove that a ball living inside this thing has non-trivial symplectic topology. But if it has a single 2 handle, then you can do it. So it could be like S2 cross R4, for example. Yeah. So it's important that it has some kind of non-trivial homology class, though. Yeah, so this will be a little bit vague, I guess, right now, but the idea for this is that there's so we define some kind of, we define some kind of construction or procedure where you take any Weinstein domain of dimension at least 6, and then you sort of manipulate it in some way, which we call the sort of sub-flexibilization, and you get some new Weinstein domain of the same dimension. And well, this thing, in particular, this thing is, as the name suggests, this thing is always subflexible, which I guess I didn't actually define that term, but so for me, subflexible just means any Weinstein domain which becomes flexible after attaching some handles, or equivalently, it's a sublevel set of a flexible Weinstein domain. So you can take any Weinstein domain and somehow produce another one which is subflexible. And this process necessarily, first of all, it necessarily kills the symplectic homology of W. But it somehow remembers the symplectic topology nevertheless, and it necessarily changes the topology, but in some sort of minimal way. So you should think it sort of adds a single 2 handle or something like that. And then, so the idea is now apply, or just consider this procedure applied to some exotic affine space. So let's say exotic C3. So here, so this is one of these exotic affine spaces constructed first by Mark McLean and then also by Abu Zaid Zaidel. Exotic affine space. And then one consequence of the construction is that this thing is sort of automatically subflexible and not flexible, and it lives in sort of standard flexible C3. And you can take, for example, the simplest example I know is you can just take this to be C3 minus a singular hypersurface, and then you attach some Weinstein 2 handle. So you take this thing, and then you kind of manipulate it in some way, which I'll kind of describe in more detail in a bit. And then that's the symplectic topology of this thing, which lives inside C3. Yeah, so are there any questions about just the statement? Or?
Well, if you're allowed to pass a sublevel set, it seems like you could throw out everything except an index 0 critical point and just prove this for a ball. Is that, what's the sort of reason that doesn't work?
Can you say that again? So you
like,
could.
Can you prove, you just have to prove this for CN because you
Oh, yeah.
throw out everything but an index 0 critical point?
Yeah, so yeah, the logic is essentially that the example implies the theorem, because once you know that just the ball has an exotic sublevel set, then essentially everything has one, because yeah, the ball lives inside every Weinstein domain. Yeah. Yeah, that's right. Okay, so I think, yeah, so in order to maybe make this a bit more concrete, it makes sense to consider what's happening here with symplectic cohomology. So let me first just kind of, yeah, question?
In the theorem, you say any flexible Weinstein domain.
Yeah.
And then with the idea, you said any Weinstein domain.
Yeah, so, well, first of all, you could say any Weinstein domain in the theorem, but then it's trivial, because if it's not flexible to start with, then of course it has a non-flexible sublevel set, it's just the whole thing. But yeah, so here, so these are sort of going in opposite directions in the sense that here you're starting with a flexible thing and then you're producing a non-flexible sublevel set, whereas here you're starting with just a manifold that you like and sort of forcing it to be a sublevel set, or sort of manipulating it so that it can be the sublevel set of something. So here you're starting with the big thing and then finding the small thing, and here you're sort of producing the small thing in some big thing, if that makes any sense. Yeah, so let me just maybe describe the sort of axioms of symplectic cohomology that will be relevant for this talk. So first of all, just so given a Weinstein domain, you get this thing called symplectic cohomology, which doesn't depend on, first of all, doesn't depend on the Morse function at all. And this is among other things, it's a unital K algebra, where K is some coefficient field. And so the kind of basic properties that will be relevant are, so first of all, it's invariant under just general symplectomorphisms of the completion. So in particular, it's invariant under Weinstein homotopy. And there's this transfer map. So if you have an exact symplectic embedding, then you get this Viterbo transfer map, which is a map of unital K algebras from the symplectic cohomology of the big thing to the symplectic cohomology of the small thing. And so in particular, I guess the sort of famous corollary of this is that if SH of the big thing vanishes, then just by looking at what happens to the unit, SH of the embedded thing also vanishes. Is it still visible over here? OK, and then sort of another basic fact is that the symplectic cohomology of any flexible Weinstein domain is necessarily trivial. So yeah, there's kind of maybe a couple of different proofs of this fact now. But it's certainly something you would expect. But in particular, so one consequence of this is that the symplectic cohomology of a subflexible Weinstein domain is also necessarily trivial by this transfer map argument. So what that says is that you can't really probe the symplectic geometry of these things just using kind of usual symplectic cohomology. That's where this idea of twisted symplectic homology comes into the story. So twisted symplectic homology is, you can think of it as just sort of symplectic homology with coefficients in some twisted, in some local system. But maybe concretely, so let me just give a concrete definition. So if you fix, so let's just fix some closed 2 form omega on W. So now the usual Floer differential, which goes into constructing symplectic homology, well, it's some count of rigid solutions to Floer's equation. So the differential of some orbit is given by some count of rigid Floer cylinders from gamma minus to gamma plus. And the twisted differential is actually almost the same thing. So you count the exact same rigid solutions to Floer's equation, except that you keep track of their homology class in some sense. So you weight them by you add some extra weight, which is the integral of this 2 form over that cylinder. Or t to the integral, where t is just some fixed element of k. So you can think of t as being either a formal variable or just like e if we're working with C coefficients. Yeah, so it's fairly easy. Yeah, so you basically you can twist every part of the floor package in the same way. So for example, continuation maps and so on. And so yeah, so you get this thing which I'll denote by twist sh of w. And yeah, it's fairly easy to see that it has all the same properties. So d squared equals 0 and so on. So yeah, so maybe I'll just sort of state some properties again. So yeah, first of all, it's also easy to show that it's actually, it only depends on the cohomology class of omega. It doesn't depend on the choice of two form representing it. But in particular, if omega is exact, then twisted sh just reduces to sort of standard sh. And so this is why I'm going to need a non-trivial cohomology class in these examples, because otherwise, I mean, this twisted sh doesn't do anything more than just standard sh. Yeah, so and it's also, I mean, essentially the same argument as with normal sh shows that this is invariant under symplectomorphisms, under just general symplectomorphisms of the completion, except now, of course, they should also respect this cohomology class. Yeah, and then you can also show, essentially, as before, you can show that the twisted symplectic cohomology of any flexible Weinstein domain for any possible twisting is necessarily trivial. But sort of the key point for this talk is that it's no longer true that the twisted symplectic cohomology of a subflexible Weinstein domain necessarily vanishes. So this thing need not vanish. Yeah, so this actually, at least I found this maybe a little bit surprising at first, because there is still, I mean, there is a transfer map in the context of twisted symplectic cohomology. So first, this seems to sort of violate this whole transfer map philosophy, which tells you that if you have something symplectically trivial, then sort of every subdomain is also trivial. But it turns out, in the transfer map on twisted symplectic cohomology, you have to think a little bit carefully about what you do with the two forms. Like you have to take sort of a two form on the ambient manifold and then the restricted two form on the submanifold. And so what's going to happen in these examples is that the sub-flexible thing has a two-dimensional cohomology class, and when you twist around that, you get something non-zero, and that's how you show that it's not flexible. But the class that you're twisting by dies when you attach these handles, and so the ambient manifold, the class isn't there anymore, so you can't twist by it, and that's why sort of sh, I mean, the ambient thing is flexible, so it has all possible twistings necessarily vanish. OK, so let's see how much time. OK, cool. So I guess, well, OK, maybe first just kind of revisiting briefly this sub-flexibilization idea. So the point is going to be that, So the subflexibilization. So first of all, so when you subflexibilize a Weinstein domain, this thing it's subflexible, so necessarily it kills its symplectic cohomology. But the point is going to be that the twisted symplectic cohomology of the subflexibilization, at least for some choice of 2 form, this is isomorphic to just the original symplectic cohomology of W. So that's why when you take this sort of exotic C3 with nontrivial symplectic cohomology, the subflexible thing necessarily has nontrivial twisted symplectic cohomology.
Say one more time, how is subflex W related to W?
Like, how's it related topologically, or
What's
just
the definition
what is it?
of
Yes. So so rather than give a definition, I want to talk about just a specific example. But let me just. Yeah, so let me say a few more things about it, and then I'm happy to talk more later. But I think it might be more enlightening to talk about an example than to give the specific definition. But roughly, roughly what we do is you take some Lefschetz fibration for W, and then you manipulate that Lefschetz fibration in some way. So essentially what we do is you take Lefschetz fibration, and then for each vanishing cycle, you sort of Dane twist it around some sphere. So in fact, yeah, so what we do is kind of, you take some Lefschetz fibration, and then for each vanishing cycle, you sort of find some fiber which intersects it once, and then I Dane twist, then I sort of attach a handle along this thing, and then I replace this vanishing cycle with itself Dane twisted twice around this fiber. So let me come back to this at the end, actually. But let me just say roughly, so roughly, so the subflexibilization of W, at least topologically, it's just diffeomorphic to W with some 2 handles attached. Yeah, but symplectically, you sort of alter each critical handle in some specific way. No, it's actually, yeah, it's actually 2 handles. So at least just smoothly. So symplectically, what's happening is that these 2 handles are somehow trapped, like at least in the 6-dimensional case, like the 3 handles are sort of trapped in these 2 handles symplectically, but smoothly they're not trapped. So there's just a bunch of extra 2 handles floating around, and yeah. So I'm being a bit vague right now, I think, but yeah. So maybe the thing right now is to first talk about an example. So at least, I mean, somehow the simplest subflexible example and maybe in some sense also sort of the universal example is, so this actually goes back to Maxime Maidansky's thesis. So this is what I'm calling Maidansky's manifold. So also, I mean, for now, let me just talk about the 6-dimensional case, but I can say a word at the end about how these ideas also kind of work in higher dimensions, but things are most transparent in dimension 6 at least. Yeah. So what is Maidansky's manifold? So for me, it's sort of most natural. These things are most naturally studied using Lefschetz fibrations. So which, at least on one hand, gives you some sort of tool for constructing manifolds in some sort of somewhat combinatorial way. So one way to describe Maidansky's manifold is as the total space of some Lefschetz fibration. So what this means is that I just need to tell you what the fiber of this Lefschetz fibration is. So it's the total space of some Lefschetz fibration where the fiber is the A2 Milnor fiber, and then I should tell you what the vanishing cycles are. And so here, so the vanishing cycles are just exact Lagrangian spheres in the fiber. And in Maidansky's manifold, these are given by, so these are the two ways of resolving the intersection point of the core Lagrangian two-spheres. So, OK, let me try to flesh this out a little bit. So first of all, so the A2 Milnor fiber is just the plumbing of two copies of the cotangent bundle of S2. So this thing, so A2, so this thing is just a plumbing of two copies of the unit disk bundle of S2. And so it has these two core S2s just sitting inside of it. And now these two things intersect at a point, and then there's two ways of resolving that point. So there's sort of positive and negative pole derivative surgery. And those give you two different Lagrangians in this guy. So maybe a slightly more concrete way to see it is using the notion of a Lefschetz bifibration. So the picture is that, so first of all, you've got Maidansky's manifold, and it has a Lefschetz fibration over the disk. And the fiber is this A2 Milnor fiber of dimension 4. And this fibration has two critical points. And then A2 Milnor fiber itself admits a Lefschetz fibration over the disk, this time with three critical points. And here the fiber is just the cylinder, so just the unit disk bundle of the circle. And so from this point of view, everything, you can see everything in terms of matching cycles. So matching cycle means you have a Lagrangian in the total space, and it projects to kind of just an embedded path in the base. So from this point of view, so the core S2s are just project to these two intervals. So these are the core Lagrangian S2s. And then V plus and V minus, they're supposed to be the two ways of resolving that intersection. You sort of go up or you go down. So you have like V plus and V minus. OK, so now, so I think the sort of key observations about this manifold are as follows. So first of all, there's the result from Maidansky's thesis, which is that this manifold has trivial symplectic cohomology. So in particular, there's no exact Lagrangian sitting inside of here. But on the other hand, there was this observation of Harris, which is that this manifold actually has a Lagrangian S3 after sort of an arbitrarily small deformation of the symplectic form. So it actually has an embedded Lagrangian S3 after sort of small, non-exact deformation of the symplectic form. It turns out that, yeah, so this sort of strongly suggests that this thing is actually sort of non-trivial symplectically. It turns out this poses some sort of technical issues because after a non-exact deformation, the resulting thing is it's not exact, but it's also not even convex at infinity. So it's not exactly even clear how to define sort of holomorphic curve invariance after deforming it, which maybe poses some slight conceptual difficulty. But anyways, at any rate, so I guess one sort of observation that we made is that this thing is subflexible, first of all. And I guess this is pretty explicit. So you start with Mayansky's manifold, and now just add one more vanishing cycle. So adding a vanishing cycle on, so I guess I didn't say, but so anytime you have one of these Weinstein Lefschetz fibrations, the total space in some natural way has a Weinstein structure. And adding a vanishing cycle has the effect of just attaching one more critical dimensional Weinstein handle. So, OK, so we just add one of the core spheres as an extra vanishing cycle. And it turns out, so this thing is not explicitly flexible, but you can apply a Hurwitz move, which is some kind of Lefschetz version of a Weinstein homotopy. So in particular, it has the effect of a Weinstein homotopy on the total space. And then you find yourself looking at this manifold. And then this thing turns out to be flexible. So this thing is actually just the flexible version of T star S3.
When you say Hurwitz move, is that supposed to be like a handle slide, or?
Yeah. So well, Hurwitz move. It's some kind of it's some manipulation of the vanishing cycles. So you roughly Dane twist one vanishing cycle around the sort of adjacent vanishing cycle. But yeah, it looks like a handle slide if you're sort of looking at if you're staring at the total space. Yeah. So. OK, so yeah, maybe now it can be a little bit more explicit about this subflexibilization construction. So here, basically, we sort of declare, so Mayansky's manifold is just the subflexibilization of T star S3, or I guess more precisely, the unit disk bundle of S3. And so in particular, so I guess in particular, this thing is, so it's not flexible. So one way to see that it's not flexible is just that its twisted symplectic cohomology is the same as the symplectic cohomology of T star S3, which is sort of well known to be non-zero. And right, so here's the Lefschetz picture. Here's the Lefschetz bifibration picture for D star S3. And then roughly, how do you go from here to Mayansky's manifold? So first, we can add a subcritical handle to the total space, which looks like a critical handle in the fiber. So you get this thing. And this thing so far, this is just T star. This is the cotangent bundle of S3 with some sort of trivial 2 handle added. And then we can add, so then we add a vanishing cycle, which is given by sort of the union of the core of this new handle with some other Lagrangian disk in the original manifold. And so we just sort of add a vanishing cycle. Or, well, maybe not add a vanishing cycle, but just observe that this sort of sphere exists. And then what you do is you Dane twist one of these vanishing cycles twice around this sphere here. And Dane twisting, in these pictures, a Dane twist of the Lagrangians looks like just kind of a half twist of these curves. So if I replace, so let me call this thing, let me just observe that there's a Lagrangian S here. And now let me replace, let's say, V minus with V minus Dane twisted twice around this sphere here. And the picture you see now is, so a double Dane twist looks like that. And now this thing is really just kind of up to deformation. This really is just Madansky's manifold. Yeah, so at any rate, this is some kind of this. Okay, this is just some sort of caricature of what the subflexibilization construction does. Is sort of you somehow take each vanishing cycle and you sort of manipulate it in some way and get some kind of exotic vanishing cycle. Yeah, so let's see. Any questions so far about this observations? Let's see. So I've got about 10 minutes. So maybe let me just start talking a little bit about maybe one strategy for computing twisted SH. So yeah, so in the context of Lefschetz fibrations, there's sort of a nice conceptual way of understanding the total space. So there's a following meta principle. Which says that, so if you want to understand the symplectic cohomology of the total space of a Lefschetz fibration, so you have some Lefschetz fibration with some fiber, some vanishing cycles, that this can be computed from the Fukaya category of the fiber with objects v1 to vk. So more precisely, there's kind of an explicit formula which takes you from this A infinity category to symplectic cohomology.
How computable is this Fukaya category?
At least, so it's at least in this example and sort of these related examples, it's pretty computable. So I mean, or more precisely, I mean, so in Madansky's example, it's kind of completely computable. But in general, well, so what's going to happen is that it's sort of after this subflexibilization procedure, I can compute the new one in terms of the old one. So it's some sort of, I might not have known what the original Fukaya category was, but at least I can relate the one after this operation to the one before the operation. So yeah, so in fact, more precisely, so there's sort of a twisted version of this meta principle, which is just some sort of natural extension. So if we fix a closed two form on the fiber M, and let's assume that call it omega, and let me assume that the support of omega is disjoint from the vanishing cycles. And then let omega tilde be the sort of extension of the pullback of omega to the total space. So the total space of this Lefschetz fibration and then the kind of twisted version of the meta principle says that the twisted symplectic cohomology of the total space of some Lefschetz fibration twisted by omega tilde, this can again be computed from the twisted Fukaya category of the fiber with objects v1 up to vk and twisted by omega. So first of all, by twisted Fukaya category, I just mean, so in the usual Fukaya category, you just count pseudo-holomorphic polygons in M with these boundary conditions. And in the twisted version, you do the exact same thing, but for each polygon, you just weight it by the integral of the 2 form over that polygon. And then it says again that there's some sort of explicit formula which takes you from this A infinity category to this twisted symplectic homology. Yeah, and then the logic here is going to be that this is something that I can understand in terms of the sort of original Fukaya category. So maybe rather than state sort of explicitly what this kind of formula is, because it's not going to be super enlightening, let me just kind of describe the key point in the case of Maidansky's manifold. So remember, you've got these 2 vanishing cycles, v plus and v minus. And then here, the key observation is the following. So I don't know, proposition. So first of all, these 2 vanishing cycles are, so I can view them as elements of the Fukaya category of the fiber, which is just A2 Milnor fiber. And these things are not isomorphic, or they're not quasi-isomorphic in the Fukaya category of the A2 Milnor fiber. This is pretty easy to see, so maybe 1. But on the other hand, they become quasi-isomorphic when you turn on this twisting 2 form. So they become quasi-isomorphic in this twisted Fukaya category. And so what that tells you is that, so after turning on this twisting, this manifold behaves exactly like just the cotangent bundle of S3, at least as far as sort of holomorphic curves can tell, or at least as far as their sort of symplectic homology can tell. Yeah, so the idea here, well, OK, so the proof of 1 is completely straightforward. It's just, you just take a test Lagrangian. So there's some Lagrangian disk T, which lives over this path here. And then you just observe that, well, the floor homology between V plus and T is trivial. I mean, they don't intersect. But on the other hand, the floor homology between V minus and T turns out to be non-zero. And so V plus and V minus are just not isomorphic in the Fukaya category. On the other hand, so just kind of vague sketch of 2. So it turns out using some sort of more spot version of the Fukaya category, which was constructed by Sheridan, there's this sort of reduces to counting strips. So it reduces to counting basically holomorphic sections. So this is a bit vague, but holomorphic sections of Maidansky's Lefschetz fibration. So sections of this thing here, in some sense, with a marked point condition. So this point has to pass through a generic. So here, this is, this was V plus, V minus, and then this point is required to pass through a generic point of V minus. OK, so I claim that if you use this more spot model, you can show that these guys are isomorphic in the Fukaya category if and only if this sort of a certain count of rigid sections is non-zero. And then, so the idea is that, so using this, there's this gluing theorem. So using Zeidel's gluing theorem, well, counting sections. So yeah, so sections of this thing. OK, so I'm interested in kind of how many sections there are. And you can just maybe write this more suggestively as just by sort of deforming the picture, maybe draw it more like that. So it's the same thing as sort of sections of this thing. And then this suggests that there should be some sort of gluing formula. So this section should be built up by sections of this part and then sections of this part. So the upshot is that, so we need to understand basically, we need to understand just sections of, so the bottom piece was sort of the standard thing, the sort of T star S3 part, and then this was sort of the new part that we glued in. So we just need to understand sort of sections of this part, this Lefschetz fibration here. And this thing, so I mean sections of this Lefschetz fibration with sort of this boundary condition. And this Lagrangian boundary condition is actually just the Clifford torus in C2. So this really, it's just Hamiltonian isotopic to just S1 cross S1 in C2. And then finally, you can make this sort of simple observation that so really everything boils down to somehow counting Maslov 2 disks on the Clifford torus, if you sort of flesh things out. And the Clifford torus has this sort of nice property that when you count Maslov disks on it, there's two families of disks, and they live in different relative homology classes. And so you can pick a two form which isolates one of those families of disks from the other one. And when you turn on that two form and you extend it to A2, it actually, so there should be sort of, somehow there's sort of two disks on this thing, but if you sort of isolate one from the other, you sort of, you get sort of 1 plus t instead of 1 plus 1, or sort of 1 minus t instead of 1 minus 1. And somehow that sort of changes the answer from being 0 to being non-zero. And that kind of, if you follow through the algebra, that sort of tells you that these things become isomorphic. Yeah, so that was a bit vague, but that's sort of the rough idea. Yeah, I'll stop there.